I don't have a great marker. You guys can't see this. I'm willing to borrow one. Yes.
You're willing? I'm willing to give you one. You have a color preference?
Nah, this should have one color. That's fine. Any color should do. I had one for 12.
I have black too.
Yeah, pretty fine. Okay. Thank you, Annette.
No problem.
Okay, so
This is
billiard
my
balls
good
flying elastically. Okay. Because they're well off the line of contact, goes through the center of gravity. Can't but go through the center of gravity. So, if we're going to talk about this generally, where we can have any M1 we want, so this is a general solution, meaning M1, M1, M2, U1 is a vector, U2 a vector, are all free. Are all free in our plane. We're still restricting it to a plane. Are all free within a plane. And obviously you could have billiard balls going in all 3 dimensions and banging into each other. We're not doing that. We are going to restrict it to a plane. This is like it's on the billiard table, alright? We're not going to worry about gravity for this solution. There's billiard balls on the table, okay? But they can go 2 dimensions now. And so to work out a solution for this, it's complex. We're going to go through it. So, what would be some equation we can put up here to relate? So what we want to know is V1 and V2, velocities after. The masses aren't going to change. Okay, the masses are going to be constant. M1 and M2 aren't changing. What we're trying to find out is, say all this stuff is given, okay? We know this stuff coming in. We know the masses of the two balls. They can be different though. And we know the 2 velocity vectors within the plane, U1 and U2. What we want to know, so we know all of this, are all free within a plane, and are known. What's that? Okay? We want V1, vector V1, and vector V2. That's what we're trying to find out. And so we need to set up equations relating M1, M2, U1, U2 to V1 and V2. Anybody have any thoughts?
M1, U1 plus M2, U2 equals M1, U1 plus
That's
M2.
true. That's true. So how would it be useful to break it into components? And the answer here is yes. Because doing it as vectors, which is true, that's how you put it, is true, but when we don't know the directions of the vectors, it makes it harder. So what we're going to do to start with is we're going to break it into the XY components. And this is just like how I asked you in the billiard ball lab. I wanted you to show that there was conservation of momentum in the Y directions. We broke it into those components. It's the same thing. So that's what we're going to start off with. Start off with M1 times U1x. Note this is not a vector anymore. This is a scalar quantity of U1 in the x direction. So we have U1x plus M2 times U2x, also a scalar quantity, equals M1 V1x plus M2 V2x. So what we're saying with this equation is that momentum is conserved in the nth direction. That's what this equation is telling us. Okay. And we can just as easily say it in the y. So we can rewrite the same guy in the y. So we have M1 U1 y plus v2x, v1y, v2y. And so seeing as we have 4 unknowns, we're going to need 4 equations. If we're going to have a solution to this. This has given us 2 of those. What else can we know about this? What else could we use to get ourselves some more equations? We got to get 2 more.
M1 U1 plus M2 U2 over M1 M2.
No, those aren't completely independent equations. Those are dependent on these. So when you have equations, you need as many equations as you have unknowns, right? They have to be independent equations. If you can do algebra one way or another and get from one of your equations to the other, it's essentially the same equation. It's not adding any more constraint. Each equation is supposed to add a constraint. This one adds the constraint of conservation of momentum in the x. That one adds the constraint of conservation of momentum in the y. The one you were talking about is another momentum equation. We've already got everything we can get out of momentum. Yes. We can use kinetic energy. This is an elastic collision, which means that kinetic energy is conserved. So yes, indeed, we can use kinetic energy to add another constraint on this. And that's what we're going to do. So we're going to take the kinetic energy beforehand. So kinetic energy of the first one, we have M1, and I'm going to do this as sort of Pythagorean theorem. It's going to be the magnitude of U1. And so the magnitude of U1 is going to be U1x squared plus U1y squared. Does everybody get how that would be equivalent to the magnitude of U squared? You're looking for mv squared for kinetic energy, right? And so we're going to divide that. Also, we're going to divide this by 2. But I'm going to plus m2 times u2x squared plus u2y squared. So I'm going to divide the whole thing by 2. And so I have m1 squared, m1 v1 squared, or m1 u1 squared plus m2 u2 squared over 2. So this is the kinetic energy beforehand. And so because kinetic energy is conserved, this has to equal m1 times v1x squared plus v1y squared plus m2 times v2x squared plus v2y squared, again, all over 2. And so this is the kinetic energy afterwards. So we've added the constraint are in X's and Y's.